Today, we're diving into a real-life chemical detective story. We're on a mission to solve a mystery that stumped some of the world's best scientists for decades. What actually makes something an acid or a base? This isn't just about beakers and complicated formulas. It's a human story. A story about struggle, about being rejected, and then, finally, about being proven right. The real drama behind the science is where our investigation truly begins. So, we're going to treat this whole thing like a classic detective case. First, we'll look at a brilliant but flawed theory. Then, new evidence is going to pop up that just doesn't fit. And finally, a new team of detectives shows up on the scene to blow the case wide open.
Okay, so what was this huge mystery all about? Well, for the longest time, chemists knew that stuff like vinegar was acidic, and stuff like soap was basic, but they just couldn't agree on one fundamental rule that explained why.
Let's meet our first detective. He's a young Swedish PhD student named Svante Arrhenius. It's 1884, and he is completely obsessed with one nagging question that's keeping him up late in the lab every single night.
This was it. This was the question that kicked everything off. Arrhenius noticed that when you put acids, bases, or salts in water, the solution could conduct electricity, but pure water or sugar water, nothing. He just knew there had to be a connection.
And here was his huge breakthrough. He suggested that when certain things hit water, they don't just, dissolve, they actually split apart, or dissociate, into these little charged particles he called ions. And it's these ions floating around freely that carry the electric current. For his time, this was a completely radical idea.
And based on that one big idea, he came up with a beautifully simple definition. Acids, he said, release a hydrogen ion, an H+ ion, in water. And a hydrogen ion is really just a proton. Bases, on the other hand, release a hydroxide ion, or OH-. Super simple, super elegant, and it explains so much of what they were seeing in the lab. But here's where the story gets a twist. His PhD committee, they thought his theory was way too out there, and they gave him the lowest possible passing grade you could get. He almost failed. But history proved him right. Almost 20 years later, he won the Nobel Prize for that exact same work. It's a perfect example of how science actually works sometimes.
But just like in any good mystery, right when you think the case is closed, some new evidence shows up that just doesn't fit the picture. The Arrhenius theory was a fantastic start, but it definitely wasn't the whole story.
The first major wrench in the works for Arrhenius came from a substance we all know, ammonia, and it presented a real paradox for his theory. Just think about it for a second. Ammonia acts exactly like a base. It feels slippery, it turns litmus paper blue, all the classic signs. But now look at the formula, NH3. There's no hydroxide, no OH group anywhere in there for it to release. So according to Arrhenius' own definition, it couldn't possibly be a base. And yet, it was.
The second problem was even bigger. You see, Arrhenius' entire theory was built on one crucial ingredient, water. But what about all the acid-base reactions that happen without any water around at all?
Take this reaction, for example. If you mix dry hydrogen chloride gas with dry ammonia gas, they react instantly and form a white solid. It's clearly an acid-base reaction, but there's no water, there's no splitting into ions. The Arrhenius theory just had no explanation for this whatsoever. So Arrhenius had laid an amazing foundation, but the case was far from closed. These new clues that didn't fit meant a bigger, better theory was needed. The mystery was getting deeper. The big break in the case came in 1923, almost 40 years after Arrhenius, and it came from two different chemists, Johannes Bronsted in Denmark and Thomas Lowry in England, who, working totally independently, came up with the exact same brilliant solution.
They realized the whole definition could be even more fundamental, even simpler. Their idea? Forget about needing water, and forget about the OH ion. It all came down to the movement of one single tiny particle, the proton, that H+ ion. In their theory, an acid is simply a proton donor, and a base is a proton acceptor. That's it. So elegant, right?
And just like that, with this new theory, the ammonia paradox is solved. Perfectly. When ammonia is in water, the ammonia molecule literally grabs a proton from a water molecule. And since ammonia accepts a proton, it is, by definition, a Bronsted-Lowry base. Case closed.
This new theory also introduced this really beautiful idea of conjugate pairs. So when an acid donates its proton, what's left behind is called its conjugate base. And when a base accepts a proton, what it turns into is its conjugate acid. They're like two sides of the same coin. An acid-base reaction is really just a proton being handed off between these pairs.
Okay, so with our second theory now on the table, let's put our two detectives side by side and deliver the final verdict on this case.
This chart makes it crystal clear, doesn't it? The Arrhenius definition is great, but it's limited. It only works for reactions in water. The Bronsted-Lowry definition is way broader. It's about proton transfer in any solvent. And crucially, you can see right there, Arrhenius couldn't explain ammonia, but Bronsted-Lowry nails it. It's not that Arrhenius was wrong. His theory was just one specific piece of a much bigger, more universal puzzle.
So why does any of this stuff matter outside of a chemistry lab? Well, because these exact proton transfer reactions are happening all around you every single day. Let's bring this whole theory right into your kitchen. You know that sour taste when you drink nimbu pani or lemon juice? That's literally citric acid donating protons to the receptors on your tongue. Got heartburn? That's just too many protons from your stomach acid. So what does an antacid do? It's a Bronsted-Lowry base that goes in there and accepts those extra protons. And that classic school science fair volcano? It's the acetic acid in vinegar donating protons to the baking soda. The big takeaway here is this. Acid-base chemistry isn't some abstract concept from a textbook. It is the fizz in your soda. It's the relief you get from an antacid. It's even how your blood keeps itself perfectly balanced. It is everywhere.
And that, really, is the final solution to our mystery. Science rarely ever moves forward in one giant flash of genius. It builds. Arrhenius laid a brilliant foundation, and then Bronsted and Lowry built on top of it to create something even more complete. Each generation gets to stand on the shoulders of the giants who came before them, which kind of makes you wonder, what mystery is out there, right now, just waiting for you to solve next?